Hello everyone, welcome to Biot-Savart Law and Applications of it. Fourth one, magnetic field due to a solenoid. Now, a solenoid is a long cylindrical coil having a large number of turns. So now, first let's say that this solenoid has n number of turns per unit length. So that means n is equals to the total number of turns per unit length, let's say L. Now, we need to find a magnetic field at a point P right here at a distance, let's say x naught from the center of this circular coil. Now, let's use what we know from the previous application of Biot-Savart law. This is on the x-axis due to this circular coil, so its magnetic field will be mu naught Ni r square by 2r cube, right? And here, well, we will find the radius later. You might think that this is the radius, but no, it is not. And this will be a small magnetic field in which we have to integrate later. Why? Because first, we have to introduce our current element. But here, we introduce a length element at a point, let's say, around here. I'm going to increase this point a little bit further. And let's say that this is of length dx. So here the number of turns per unit length will be n by dx. And from here we will draw a line vertically down, let's say at a point M, which will be of distance x. Now here, then we join this dx to p, making radius r. This will be theta, this will be alpha. And here, this application for a solenoid is a bit different because, well, you don't have to use ideal sine theta by r square because you already have this, and you need to just integrate this by replacing these variables with constants, because here radius, the small radius, is all constant, because if you choose at any other points, this radius will also change like that. Similarly with the angle as well, but thankfully we don't have the angle right here. And the current will be the same, so we only have to change r. So here, let's find the total number of turns from here, which will be n dx. N will be equals to n dx. So dB will be equals to mu naught n dx I r square by 2r cube. Now in this figure, let's find what the constant is. Well, here, of course, the radius of this circular coil will be constant. So let's put everyone in terms of this r and using this angle alpha right here. So from this triangle we can use trigonometry, and here we need to find in terms of r with this alpha, which is r by r, perpendicular by hypotenuse, so this is sine alpha. That means that r sine alpha is equals to r, finally meaning r is equals to r cosec alpha. Now let's also find dx here, because again this can also be, well, no, we need to find dx in terms of r as well in order to have a nice equation that we can simplify easily. So from here, let's find the distance x. So obviously this shape, we can do nothing with it at the moment. So let's just take this whole thing. So let's take this triangle's base. If this whole thing is x naught and this is x, meaning that this distance is x naught minus x, and we'll find it in terms of r, this big R right here. So with this alpha, we know that this is perpendicular by base. So perpendicular by base, meaning tan alpha is equals to r by x naught minus x, meaning we have x naught minus x equals to r cot alpha, and we just differentiate both sides. And since x naught is a constant for any given point, because the point in which we have to find the distance from origin doesn't change, minus dx will be equals to r, which is a constant, minus cos x square alpha, I'll write the minus right here, d alpha. Now let's put r and dx in this equation right here. So we get db is equals to mu naught n by 2r cube. So we have our dx, this minus minus cancels, of course, r cos x square alpha d alpha, and I'll write I here as well, r square, oh wait, r cube, meaning this is r cube cosec cube alpha. So here we have r square and r, which is r cube, so these all cancels, cosec square alpha and cosec cube alpha cancels, leaving us with cosec alpha, and of course 1 by cosec alpha is just sine alpha. So dB is equals to mu naught ni by 2 sine alpha by d alpha. And now we will have to integrate both sides. So I'll write it over here, integrating dB. And like in the previous application of straight conductor, we are in the alpha world for the integration part. So we'll have to find the range of alpha from where it goes from the least to the maximum point. So the least point we can take is over here at 0, in which the alpha's angle, we have to take from dx, and the dx least position would be at the circumference right here. So this is our alpha 1, and the max position it can be is at the other end. So this big one will be alpha 2. So now here B, it goes from alpha 1 to alpha 2. And now mu naught ni by 2 is a constant, and sine alpha's integration is minus cos alpha, going from alpha 2 to alpha 1. Now we can use a definite integral property right here, in which this minus sign changes the limit, the upper and lower limit, which just basically swaps those both, becoming cos alpha 1 to alpha 2. Therefore the magnetic field is mu naught ni by 2 cos alpha 1 minus cos alpha 2. Now we again have to take two cases. Let's use the frequent one used in numericals, which is for infinite length of the solenoid. Meaning that if this is infinite length, then we will have to find alpha 1 and alpha 2. So here alpha 1, if you stretch it far, so far, then it will almost become 0. And here for alpha 2, if you stretch this very far, this angle right here, from this point, it will almost become 180 degrees or pi. So if you put it in here, cos alpha 1 is 1, cos 0 is 1, and cos 180 is negative 1. Minus minus plus, this becomes 2, and these two cancels, therefore B will be equals to mu naught and I. This is a very very frequently used expression for numericals. There is also another case when one of the length is infinite. So when one of the length is infinite, when the point is on one side, let's just take point P on this side right here, right? So that means, well, first let's find the easy one. If you put this right over here, then this whole thing will be 90 degrees, and cos alpha 1, well, if you put it right here, then this would almost be 0. So putting it